Deep within the quiet stillness of deep space, the cosmos appears serene, orderly, and eternal. Yet beneath this tranquil surface lies a disquieting truth that keeps theoretical physicists awake at night. The emptiness of space might not be empty, nor is it guaranteed to be permanent. We exist within a cosmic illusion of absolute stability, resting upon a physical foundation that could, in theory, collapse without warning. To understand this hidden fragility, we must first reimagine what we mean by a vacuum. In everyday language, a vacuum is simply an empty container stripped of all matter and air. But in quantum physics, space is never truly empty. It is permeated by fundamental energy fields that dictate how particles interact and how matter acquires mass. A true vacuum represents the lowest possible energy state of space, a state of absolute equilibrium where no further energy can be shed. Enter the concept of the false vacuum, a state where an energy field appears stable, but actually resides at a higher energy configuration than its true minimum. Imagine a ball resting in a shallow hollow high up on a steep mountainside. To an observer standing beside it, the ball appears completely still and firmly at rest. Yet it sits far above the true valley floor below, possessing latent potential energy just waiting to be unleashed. This strange potential was brought into sharp focus with the historic discovery of the Higgs boson at the Large Hadron Collider in 2012. By measuring the precise mass of this elusive particle, physicists unlocked a key variable in the fundamental framework known as the Standard Model of particle physics. The Higgs Field is responsible for granting mass to elementary particles, giving structure to atoms, stars, and living beings. But those measurements revealed something startling about our cosmos. Calculations based on the mass of the Higgs boson suggest that our universe currently resides in a metastable state. The Higgs field is not at its absolute lowest energy level, but is trapped in a false vacuum state. It has remained stable for 13.8 billion years, allowing galaxies to form, stars to burn, and life to emerge. Yet this stability might only be temporary, held in place by an energy barrier that separates our current state from a deeper, true vacuum. In classical physics, a ball perched in a hilltop hollow would remain there forever unless pushed over the edge by an external force. Quantum mechanics, however, operates under entirely different rules. Through a phenomenon known as quantum tunneling, particles can overcome seemingly insurmountable energy barriers simply by vanishing from one side and reappearing on the other. A field in a false vacuum does not need to be pushed over the barrier. It can spontaneously tunnel right through it. If a quantum tunneling event were to occur anywhere in the cosmos, even in the loneliest void between galaxies, the consequences would be instantaneous and absolute. A tiny microscopic bubble of true vacuum would spring into existence. Inside this bubble, the laws of physics would be fundamentally rewritten. The Higgs field would settle into its lowest possible energy state, instantly shifting the fundamental forces that hold our physical reality together. Driven by the enormous difference in energy between the false vacuum and the true vacuum, this newly formed bubble would expand outward in every direction at the speed of light. The expanding wall of the bubble would act as an unstoppable cosmic shockwave, consuming everything in its path. Because nothing can travel faster than light, there would be no advance warning, no telescope could detect its approach, and no signal could forewarn an endangered world. As the boundary of the true vacuum passes through space, atomic structure itself would instantly disintegrate. The altered Higgs field would drastically change the masses of fundamental particles like electrons and quarks. Without the familiar forces holding atoms together, chemical bonds would shatter, and complex matter would dissolve into a chaotic soup of raw energy and unfamiliar particles. Stars, planets, and human observers would cease to exist in an imperceptible fraction of a second. Physicists refer to this dramatic transformation as a cosmic phase transition. Just as liquid water freezes into ice or boils into steam when its environment reaches a critical threshold, the space fabric of our universe would undergo a structural shift. But unlike water changing state, this transition would alter the very parameters of nature. The fundamental constants that govern electricity, magnetism, and gravity would be permanently redefined within the expanding sphere. The mathematical foundation for false vacuum decay was first articulated in the late 20th century by theoretical physicists studying quantum field theory. Sidney Coleman and Frank DeLucia demonstrated that such a decay event is mathematically permissible within the equations of general relativity and quantum mechanics. Their pioneering work transformed what seemed like science fiction into a rigorous area of cosmological investigation, forcing scientists to confront the ultimate longevity of our universe. Yet critical questions remain unresolved as researchers refine their measurements of subatomic particles. Is our current vacuum state truly metastable, or could subtle corrections in quantum gravity reveal that we reside in a completely stable, true vacuum? Precise measurements of top quark mass and Higgs boson mass place our cosmos right on the razor-edge boundary between absolute stability and potential metastability, leaving the ultimate answer suspended in scientific debate. Even if our universe is resting in a false vacuum, the timescale for false vacuum decay is extraordinarily, unimaginably vast. The probability of a quantum tunneling event occurring in any given region of space during our lifetimes is exponentially close to zero. Physicists estimate that the expected lifespan of our false vacuum state far exceeds tens of billions of years, dwarfing the current age of the cosmos and extending well beyond the life cycles of stars. Furthermore, the accelerated expansion of the universe driven by dark energy introduces another fascinating dynamic into this cosmic equation. Because space itself is stretching apart at an accelerating rate, distant regions of the cosmos are receding from us faster than light can travel across the intervening void. Even if a bubble of true vacuum were to nucleate in a far-flung galaxy billions of light years away, cosmic expansion might prevent it from ever reaching us. Pondering false vacuum decay reveals the profound beauty and fragility of the cosmos we inhabit. The intricate complexity of life, stars, and galaxies relies entirely upon delicate balances established in the earliest moments after the Big Bang. That our universe exists in a state capable of supporting conscious observers for billions of years highlights the breathtaking architecture of physical law, where subtle subatomic values shape the fate of entire galaxies. Could future discoveries in theoretical physics rewrite this terrifying script once again? Many scientists suspect that the Standard Model, while extraordinarily successful, is an incomplete picture of reality. Incorporating dark matter, dark energy, and quantum gravity into a unified theory may demonstrate that the energy landscape of the cosmos is far more secure than current models suggest, resolving the paradox of our precarious vacuum. For now, false vacuum decay serves as a powerful testament to the relentless human desire to comprehend the universe at its most fundamental level. By peering through powerful telescopes and smashing subatomic particles together in massive colliders, humanity continues to unlock the deepest secrets of space and time. We learn that the cosmic stage is not a static background, but a dynamic, evolving environment governed by quantum rules. As we look out into the night sky at the glittering sea of ancient starlight, we are reminded of the grandeur and mystery that envelops our world. The cosmic vault holds secrets far grander than our daily lives, urging us to keep asking fundamental questions about where we came from and where our universe is heading. In understanding the delicate balance of our cosmos, we gain a deeper appreciation for the precious, miraculous epic of cosmic history we inhabit.